Hello everyone and welcome back to this series of videos on the Solow growth model. Lately we've been focusing on the Cobb-Douglas production function and how it satisfies the main assumptions of the Solow growth model. Specifically in this video we are going to focus on the diminishing marginal product of labor and derive it algebraically. So what does diminishing marginal product mean? Basically, if we increase the number of workers that are hired, this is going to lead to an increase in the production, an increase in the output, but at a diminishing rate, meaning that each additional worker is going to add less output to the total stock than the previous worker that was hired before them. Let's begin by deriving the derivative of the marginal product of labor. So we've already derived in a previous video the marginal product of labor itself as the first derivative of output with respect to labor. And the equation that we obtained looked like something like this. And what we're going to do now is to take the second derivative of the output function with respect to labor, which is the same thing as taking the first derivative of the marginal product of labor function with respect to labor again. So we're going to take this function and differentiate it with respect to labor. Following the chain rule, we know that we have to take the exponent, take it down, and then subtract 1 from it. So what we're going to obtain will be minus alpha times 1 minus alpha k to the power of alpha, as we're keeping labor constant. Otherwise, we would not be able to identify the proper effect of an additional worker on output if we kept on changing capital together with it as well, times labor minus alpha to the power of minus alpha minus 1. So let's look into this. 1 minus alpha we know is going to be positive as alpha is included between 0 and 1. However, minus alpha is going to be negative. And the two factor inputs are going to be positive again, because if we had a negative factor input, we would have 0 output, but we don't want that. And also it doesn't make sense to have a negative factor input. However, since we have a negative here, minus times plus is minus, times plus is minus, times plus is minus. Hence, overall, the derivative of our marginal product is going to be negative. It's going to be less than 0. Let's look at an algebraic and a calculation example to make more sense out of it. So we are going to look at what happens to the marginal product of labor if labor used in the production increased by 10%. How we are going to do it? So we're going to make a ratio between the new marginal product of labor, so including the change in labor, which is going to be a plus 0.1 L. And then we're going to take a ratio with the old marginal product of labor, which is this equation here. So we are going to do 1 minus alpha k to the power of alpha L plus change in L to the power of minus alpha. And then we're going to put in the denominator the original equation. So here, as we said, this is going to be 0.1 L. So in total, this is going to be 1.1 L. And if we simplify other factors into our equation, the 1 minus alpha simplifies out, cancels out, k to the power of alpha cancels out as well. And we know that we can rewrite all of this according to the laws of indices in a unique parenthesis with the power of minus alpha. So let's do that. We are going to obtain 1.1 L over L to the power of minus alpha. And again, we're going to simplify out the L's. And we know that alpha is equal to 0.3. So our result is going to be 1.1 to the power of minus 0.3, or 1 over 1.1 to the power of 0.3. And if you plug this into your calculator, you're going to obtain 0.972, which is the ratio between the new marginal product of labor and the old marginal product of labor. And since it's less than 1, it means that the MPL decreased following the additional labor. What does this mean intuitively? We can conclude that the new marginal product of labor is indeed lower, which means that with higher level of labor, marginal product of labor is lower. And this is the exact definition of diminishing MPL. Maybe let's think about this, what it would mean in a real life scenario. So we said that we are keeping capital constant. So let's say we have 2 machines in our capital stock, and we have each machine, let's say, is working at full capacity. We have 4 workers per each machine. Let's say that now we decide to hire 2 more workers with the same number of machines as before. Both machines are going to be slightly overused. And these 2 new workers, let's say, they will not add as much value as the additional workers that were put in place before. We could also even consider the increase by 1 worker, since we're actually talking about a marginal increase in labor. So if we add 1 more worker, this machine is going to be slightly overused. And this additional worker with the same number of machines as before is not going to produce as much output as, for example, if we consider the example of the previous time period than this, where 1 machine was used at full capacity, but here, as we can see, there is a worker missing that was added here, and allowed the increase in output in the first change to be greater than the increase in output in the second change, for the simple fact that now we have a little bit of overcrowded environment here at this machine. Thank you very much for listening and for watching this video, and I hope I will see you in the next one, where we're going to run through constant returns to scale, our next Cobb-Douglas assumption.